So as Professor Sharma mentioned, it's very important to have a proper bias for an analog circuit. The reason is that because analog circuit usually deals with a lot of specifications, and to meet all these specifications it's very difficult actually to design the circuit. Otherwise we could just have a few specifications, say for example delay, power, area. So that makes the design simpler. But in analog we deal with a lot of things, and usually the nature is analog, of course forgetting about what quantums brings into the picture, but generally when we are talking about analog and digital, nature is analog. So to get the signals from nature and then bring it into the electronics, we need analog front end, we need sensor, and because of this we need a lot of things to be incorporated in that interface to permit us to extract the signal from nature, removing all noises from that signal, and usually the signal which is in the nature is a small signal. Its amplitude is very small. So we need a precise system which is able to extract the signal. So that's why this system should be designed properly with a lot of desired specifications. I don't want to enter into the details, but what is important is the specification should be long lasting. They should not deviate from whatever we want. So that's why generating a bias for a circuit is very important. If bias point of an analog circuit changes, you know that all specifications will change. So that's why stability and tolerance of bias to different sources of noise, different sort of variation is an important issue. So essentially the goal in generating reference current or reference voltage is to generate some reference and then generate all the biases we want from that reference with proper accuracy. And then in this way we can bias the entire circuit. So some of the sources of variations we have, like supply voltage variations, fabrication process variations, temperature variations. So it depends how we design the circuit and how much accuracy do we need. So we want to generate a reference. So sometimes we can generate a reference voltage and then generate a reference current from reference voltage. So these two are actually dependent. So what is the concept? The basic concept is we have some set of reference parameters, so we will talk about them afterwards. From these reference parameters, we generate some reference current, for example, and then we generate whatever current we want. So this is a straightforward methodology. A very simple circuit is that if you put a resistor, connect it to a diode connected MOS transistor, and then put them between ground and VDD. So this is a simple circuit for generating a bias. And then the current which is generated in the transistor can be mirrored. You know what is the mirroring? Mirroring is that we have a current in some branch and then we copy this current in different branches. This is called mirroring. Mirror it and give it to different parts of the circuit. So in this way we bias the circuit with a current, not voltage. Essentially, I would say that the most common approach is biasing with a current, not voltage, but we need voltage to generate the current. Another approach is that instead of relying on some parameters which will dictate some specific reference for us and then generating output, let us have a self-biased approach. In self-biased approach, though we connect the circuit to VDD, but actually the current which is generated in the reference circuit is not a function of VDD. It's self-bias. If VDD changes, it doesn't change. It biases itself. So the second approach is that we generate a feedback. So we will generate some reference current IRF1. From IRF1 we will generate IRF2. From IRF2 we have a feedback which generates IRF1. So you know that from mathematics, if we have a system which is having this feedback in this way, so can be self-biased. And that concept means that we can generate references which are independent of VDD. And then of course the mirroring part remains as it is. So we will look at these two aspects together and then see what are the benefits with the second aspect. Before going with the first simple reference generator, let us just give you an example. This is a very simple circuit, a basic circuit by which you can generate a reference current. We call this current IREF. And then by a simple mirroring, you can generate as much as current you want from it. So this is a very simple and easy method to do it. Now what are the problems? Let us give you an example. I think this is very straightforward and all of you know how the current is generated in this branch. This current will be a function of VDD, will be a function of size of this transistor and a function of value of resistor R. So the parameters I talked about them is W upon L, process parameters, R and VDD. So here all of them contribute and determine value of the current. If any one of them changes, the value of current will change. So let us give an example to get an idea of why do we want a precise biasing. Suppose we have a VDD of 2 volt and we have I reference 10 microamp. Means that what we want is to generate a reference current of 10 microamp. Suppose transistor has been biased in such a way VGS is equal to 1 volt. Okay, so this is actually VGS changes, but let us consider VGS is 1 volt and then so accordingly we will get around R is equal to 100K to achieve this current. And aspect ratio of transistor will be around 1 upon 6.3. This is just a crude example I want to give you to get an idea of how much biasing may change. And suppose threshold voltage of transistor also is 0.3 volt. Now suppose if VDD changes by amount of 10%. Threshold voltage changes by amount of 80 millivolt, which may happen in the process variations when we are going from a worst case corner to the another worst case corner. So 80 millivolt is not a very strange value. And suppose mu Cox changes 15%. Now what will happen? If you do all calculation, obtain value of I don't enter into the details, you will get IREF is equal to 18.25 microamp. What does it mean? 82% increase in the current. And actually 82% is too much. Because if you have a bias point in the current of I and now your current becomes 2I, either your transistor in some part of the circuit may be driven into ohmic region or vice versa, some parts of the circuit may go into off region. So that's why it's very important. And in analog design, always we deal with all these variations. So it is not easy to escape from them. So let us see how we can omit one by one. So one way of omitting some of the parameters is to use self-bias approach. In self-bias approach, at least we omit effect of VDD, because now circuit can be biased by itself. So one of the very famous and basic circuits for generating a self-bias current is constant GM current reference generator. So as you see, this circuit actually has some sort of feedback inherently. What we do is that here we have a loop consists of VGS of transistors M3 and M4 and resistor R. So this is a loop. This is the second method I showed you in the previous slide. So we will generate a feedback from IREF1 to IREF2 or from IREF2 to IREF1. It depends which one you get as a reference. So this circuit generates a self-bias mechanism. So this is the main equation which is valid in this loop, and one more equation is IREF1 is equal to IREF2, and you have relation between IREF and VSG, so you will just replace. So you will have one equation for IREF which is independent of VDD. I don't enter into the details, just you replace for VSG4 and VSG3 by relation between the relation for I instead of VSG. So if you replace for I, you will have one equation which determines value of IREF, which is IREF1 or IREF2 equal to IREF, versus these parameters, aspect ratio of transistors, value of R. Now suppose we have same aspect ratio for NMOS transistors, so these two aspect ratio of M2 to M1, that of M1 is 1, and aspect ratio of M4 to M3 is M square, and M is greater than 1. So can you tell me why M should be greater than 1? I have kept this condition here. So M is just some variable. I want to develop a relation for this current. And as you observe here, at the final relation, M appears as M minus 1 square in the relation for IREF. So do I need to keep M greater than 1? Means that do I need to keep aspect ratio of M4 to aspect ratio of M3 to be greater than 1? So look at this relation. What does it tell you? What does it impose on this circuit? See, this is our IREF2, right? So IREF2 is a current which flows through the branches. So it's a positive value. R also is a positive value. So this term is a positive value. So if you have an equation and left side is a positive value plus some variable equal to some other variable, then what is the result? Suppose I write A plus X is equal to Y and A greater than 0. So what's the relation now between X and Y? So it implies some constraint between X and Y. Yes? If I put A greater than 0, so does it mean any value of X and Y will satisfy this? Yes, Y should be greater than X. So here we have a positive term. So what does it say? So it says that, right, VSG3 should be greater than VSG4. That is a very important point in biasing here. Otherwise your circuit cannot get biased. And to make it, now look what another equation implies. IREF1 should be equal to IREF2. because aspect ratio of these two transistors are same, M1 and M2 have same aspect ratio. They have same current, right? They have same VGS. And because to have same current through M3 and M4 accordingly, we should look what is the relation between VSG4 and VSG3. VSG4 is less than M3, but both of them should conduct same current, right? So if we give a less aspect ratio to M4 than M3, then this circuit is impossible to get biased. So it's very important reference circuit itself to get biased properly. So that's why we need to have M greater than 1. So now if you write equations, it's very easy. As I told you, just in this equation you replace for VSG4 and VSG3 versus IREF. Then you will get this relation. This is the relation for reference current that you can generate. So it's a function of M, it's a function of R, it's a function of mu C ox, and this is a function of aspect ratio of this transistor, M4. And of course, M3 is a function of M4 and M. So it is inherently is here. And because we consider this aspect ratio ratio of aspect ratios is 1, so we got this relation. Now if you look, there is no VDD here. So at least in one step, we have got rid of VDD effect. And the next thing is that because this M is ratio of aspect ratios, so if we have some changes in the length or width of transistors because of temperature, because of process, this ratio won't change. Ratio of aspect ratios. So M is almost a constant value. But still, or if it is an on-chip resistor, it will change with the process. Mu Cox will change with the process. But at least here we expect to have less variation than 80% that we observed in the simple example. Of course, here I have considered output impedance of these transistors is very high. So that's why in the relation for I have just considered a square law relation. No impact of VDS on I. Otherwise, this equation won't be as simple as possible, and then it will have a function term which is a function of VDD. So that's why it's very important these transistors to have a low output impedance. So one way of doing that is to change this simple common source configuration to a cascade configuration. We can have another modified version of this circuit which uses cascade configurations. And next thing is, we can itself play with the value of I. How I affects on the output impedance? Yes, it will affect, right. So how I can control output impedance by the value of current? Is there any relation between output impedance and value of current in a transistor? It is valid. Say, let us talk about MOS transistor. In an MOS transistor, is there any relation between bias current or drain current and output impedance? Yeah, there is. So, what is that relation? Suppose if I reduce the drain current of a transistor without changing anything else, what do you expect to observe in the output impedance? Any change do you observe? If I reduce current, it will increase, right, right. So in an MOS transistor, if I reduce current, output impedance will increase. So if I use this circuit with a small bias current, so means that set IREF at a very small value, even this circuit will show a good output impedance. And actually that is desired, because nobody wants to design a reference current with a value of say 1 milliamp. Unnecessary, it's dissipating current. Instead, I can design a reference current with a value of 1 microamp and then mirror it. And when I am using mirror, then there I can have amplification in the consequent stages. One more thing is that if you look, there is an interesting fact here that one solution, because now we have a closed loop circuit, so that's why it is having a self-biased solution for the current. But one more solution exists, which is IRF equal to 0, because this circuit can get stuck in off region, means that all transistor can be in off region, right? Suppose all VGS values can be 0 and all currents can be 0. So this is very important to avoid this circuit to get stuck in that low bias current or zero bias current. Practically it may not happen. Practically, because when you have a circuit on a chip or even a discrete circuit, there are many sources of noise, and because of that you have some current which is flowing, and actually that helps this circuit to come out of that dead bias point and converges to this bias point. However, for the sake of reliability, always we should put a startup on the chip, because if this circuit doesn't work, you know what happens? The entire chip won't work, even though everything is correct. That's why bias is very important. Of course, we do some shortcuts, like we provide extra pins. If it doesn't work, at least we apply the current from outside and then let the chip work. So that's why it's very, but finally we don't want to keep those additional pins. Packaging is very important, size of package, so we don't want to have additional pins. So we put a startup on the circuit on the chip. So startup inject some current into the circuit. So there is another module called the startup circuit. It injects some current into this circuit, and then when it starts working, after some time this voltage will reduce, this voltage will increase, and then this change will drive the startup to be off. So startup will work only if this circuit is not biased well. Means that this node is very high, so that these transistors cannot get on. This node is very low, so that these two NMOS transistors cannot be on. There is a bipolar version of this circuit. That's why it is called beta multiplier sometimes, because actually this circuit can behave like a positive feedback under some conditions, and then if we replace all these MOS transistors by bipolar transistors, beta of the transistor will get multiplied, and then finally the circuit will enter into the either this self-biased operating point, or it may lead to burning these transistors due to excess current which is generated because of positive feedback. So why is it called constant GM current reference? So here I have repeated the same relation we got for reference current. Now if you want to design, for example, a reference current generator, so suppose with the value of 10 microamp that we wanted last time. So just you will replace the values, you decide about M, you decide about R, you decide about aspect ratios, and then you will get the value of current. So there are many factors how to decide about values. We will not talk about them here. But anyway, so you can choose, and then look at what is the GM of this transistor. I have, you know what is GM, right? Delta ID by delta VGS, or derivative of ID with respect to VGS when VDS is constant. That's very important, because ID also changes with VDS. Fine. So now we obtain the value of GM. By the way, all these transistors are in saturation region. So now GM3 will be this. And if you look, now there is no transistor process parameter except R, which is a process parameter, but it's not a transistor process parameter. If we could have R off chip, then there would not be any parameter which depends on the process. So that's why it is called constant GM current reference. Otherwise not, because R itself for on-chip resistors, it changes across process corners. And actually this is one of the main bottlenecks. If you could achieve a very almost constant R on chip, then we would generate a very nice current reference generators, because we can get rid of these parameters. But this R always generates variation in the reference currents. There are,
even if it is off chip, then because of temperature it may
yeah, but I agree. I mean, ideally always everything changes, but if you look at the amount of change you observe in a discrete resistor, is much less than an on-chip, because an on-chip resistor, see, off-chip resistor observe ambient temperature, but on-chip resistors senses chip temperature. Sometimes it goes above 100. So that's why we get a lot of variation. And the second thing is not only the matter of temperature. Process itself, suppose if it's a poly resistor, if the doping in the poly changes, then the sheet resistance will change easily. So it's very difficult to achieve a good on-chip stable resistor. Okay, so we have still sensitivity to process parameters, but because I want to enter into the band gap concept, here I have considered sensitivity to temperature. So temperature coefficient is a very important parameter, and one of the figure of merits for looking at how a bias generator is generating a current or voltage which changes with temperature. So it is actually relative variation. If you get derivative of the current with respect to the temperature and divide it by current, it is called temperature coefficient. So now look at like this beta multiplier or constant GM current source. So this is expression for IREF, and then we can get value of temperature coefficient. So two parameters are changing with temperature. One is value of resistor and one is Kp. Kp is the same as mu Pcox. Instead of mu Pcox, I have called it Kp, which is usually called in the literature, is called Kp. So if you get derivative divide by I, you will get this relation. So it's just a mathematical analysis, nothing specific. Again, by writing detailed relations for mobility, you can reach to this relation. M is a process parameter. And this is for a typical polyresistor, which we observe 1000 ppm per degree centigrade. ppm actually is part per million. Means that whatever you have, multiply by 10 to the power 6. So it's part per million. So now, one example, suppose at T equal to 300 degree Kelvin, and suppose temperature coefficient, one of the typical values is 3000. Now if we want to design a bias generator which is working from 20 to 70, amount of variation will be 15% with respect to temperature only. But still 15% is not a small value for many applications. Can you tell me in one application, doesn't matter it is current or voltage, 15% variation is too high. Have you dealt with any application? See, one simple example is ADC. In ADCs, 15% is too much for a reference. You will lose many bits. At least you may lose 3 or 4 bits out of a, say, 12-bit ADC. So it's a very important characteristics for ADCs. And of course, it depends on many other applications. In sensor applications also, we may lose many things. So here, exactly just the same circuit, but what I have done, just I have changed everything to cascade. to get a better relation for IREF, because we need to neglect the effect of VDS, otherwise IREF will depend on VDD. So this is the same circuit, but just replacing each transistor by a cascade version of that. And you know that this connection is called wide swing cascade current mirror. It's a special case of cascade. I don't want to enter, but just this is the bias loop. This is bias generation for these nodes that we need. And this is that startup circuit I talked about. You know, how does it work? Suppose this circuit has entered into that dead bias point. So all transistors are off. When they are off means that these gate voltages are very low. And gate voltages of NMOS transistor. And gate voltages of PMOS transistors is very high. Now what happens is that because this is low, this M15 is off. So now what happens is that this is like a resistor connected to VDD. So because of this, this node potential will rise. And because it rises, these transistors, NMOS transistors, M17 and M18, start conducting the current. When they conduct the current, so these node voltages will come down. As soon as they come down, these transistors will be on. So then these transistors will be on, and then this node voltage will increase. When this increases, so this transistor will be on. Now this node will come down. And because the nodes comes down, these transistors will be off. And then this connection will be stopped. So this is just an example. So what is important is we have always a bias loop, and we need some additional circuitry to bias internal nodes if we are using cascade, and this is the startup. So this circuit will be enough to implement on a chip, and it will work. Of course, I should tell you most of the time without a startup it is working. But as I discussed, the problem is that still we have effect of process variation and effect of temperature. Of course, never we can omit effect of temperature, but at least we can reduce effect of temperature. So going one step forward towards generating a very nice bias generator, now we are talking about a voltage reference generator. Because if we have a voltage reference generator, we can generate current from that voltage also. So that bandgap reference, I think many of you know about it, right? Do you know about bandgap? Okay, so I will explain from the beginning. What is the concept behind bandgap? Forget about this. Look at this concept. I want to generate a reference which will be a function of two terms. Okay? One of these terms is VB of a bipolar transistor, and one of them is a VT, thermal voltage. Why these two? First of all, here there is not any other thing. Second thing is, VT, you know, increases with temperature, VBE reduces with temperature. So if I choose the coefficient of alpha 1 and alpha 2 in such a way, the temperature coefficient of this VREF is 0 at the temperature I want, for example 27 or 25, then I will have a very nice reference generator. Why? Suppose this is your temperature axis and this is VREF, and this is say 300 Kelvin. Now if you generate a reference generator in such a way, its thermal coefficient at this point is 0. So means that here is the either maximum or minimum value of the VREF. So then you will observe minimum variation at around this temperature with respect to temperature. When the slope is 0, means that sensitivity is 0, so I will get the minimum variation or minimum sensitivity. Actually at this point sensitivity is 0 because the slope is 0. So, and the next thing is that here I don't have anything specific which will affect on the value of reference voltage. We will show that it won't be a function of process parameters. It will be, like it will be a function of silicon band gap. But silicon band gap doesn't change as such, right? It changes with temperature, but it changes very slowly with the temperature. So it is a good candidate for generating a fixed and stable reference for the entire circuit. So we use the silicon band gap voltage to generate this. And why this silicon band gap? It can be explained. Okay, so how we can implement this? If you look, I can generate Vt ln n, right? Here I have written Vt ln n. Actually it is K1 VBE plus K2 Vt. But how we can generate this K2? This is actually a function of some parameter which are not a function of process parameter. How? Suppose I have two bipolar transistors. This is VBE of one of them and this is VBE of the second one. You know that VBE of bipolar transistor is given by, do you know the relation between VBE and collector current in a bipolar transistor? Do you know? This is a bipolar transistor. So this is VBE, this is IC. How IC is related to VBE? Do you know? There is an exponential relation. Again here I have neglected effect of collector emitter. So that's why almost in the active region of bipolar transistor this relation is valid. Is is one of the parameters in bipolar transistor which depends on the area of emitter. I call it A under subscript E, area of emitter. Now what happens? Suppose we have two transistors, bipolar transistor, and both are conducting same current. But area of one of them is n times of the other. This is similar to the situation which happened in the case of constant GM current source. We had a loop with a resistor in the loop and there was a difference between these two VSG, source gate voltages, and because of that there was a difference between aspect ratios. So here what we do is consider we have two bipolar transistors. They have same current. The only difference is if area of one emitter in one transistor is A, in the second one is NA. Let us use capital N. So NA. Now, what will be the relation for the VBE? From this, VBE is Vt ln IC upon Is. So, VBE is equal to Vt ln IC upon Is. Is is proportional to area. So, suppose for transistor 1, I use subscript 1. So, it will be like this. Vt is thermal voltage constant, Kt upon Q. Ic is collector current, is same for both. So, VBE2 will be equal to Vt ln IC upon Is2. Now, we will have this 2. Now, if I use this term, if I can generate VBE1 minus VBE2 somehow, okay, suppose, then this will be Vt ln IC upon Is1 into Is2 upon Ic, right? So, this 2 Ic will cancel, and then because Is is equal to, is proportional to A, so Is2 upon IS1 is equal to N, which was the ratio of area. So this will be VT ln N. So it's very interesting. We can generate a voltage which is proportional to temperature and it is independent of any process parameter, right? Because Vt is just a function of temperature. It's kBT upon Q. Kb is Boltzmann constant and N is the ratio of area, which is not changing with process. We can fabricate a transistor with a given value of area for the emitter. So if I can generate this difference somehow and force two transistors to have same collector current, then I can develop this Vt ln N. So this is the basic of bandgap reference generator. And N is a constant value. We call this PTAT voltage. This term you may have seen in some literatures. We have PTAT current also. So PTAT means proportional to absolute temperature. You see from this relation, this voltage is proportional to absolute temperature, T. Okay, so now coming back to concept of bandgap. So variation of Vt with temperature is around 87 millivolt per degree Kelvin. This is per degree Kelvin. It is not shown here. Okay, so this is upon K, upon degree Kelvin, upon. This you just correct it. And the variation of VBE with temperature is almost around minus 1.5 millivolt per degree Kelvin. So if we choose, for example, at this temperature, if we choose these two coefficients to be like this, alpha 1 to be 1, alpha 2 ln N to be 17.2, the temperature coefficient will be exactly 0. So what we want is to choose this coefficient, alpha 1 and alpha 2 and N, in such a way temperature coefficient at room temperature or any other temperature we would like to be 0. So in that case, that would be very interesting and it can be shown in all cases always the value of reference under this condition. This condition of coefficients will be 1.25 volt. If you have looked at many ADCs, they have a reference of 1.25. That is actually has come from this. They have an on-chip bandgap generator which generates this reference. And they use it for a reference for the ADC. That is the base reference which is used for ADCs. And when they want to generate a higher or lower reference, they will just use the divider to generate, or voltage multiplier to generate other values from this reference. This is a very well stable value. It doesn't depend on any process parameter. It just is a function of temperature. But the amount of variation you may get across, say, 100 degrees centigrade, it may not be more than 2-3%. So that's a very nice stable reference generator. And still nowadays it is used. I mean, it's a very well known concept and it works well. Only that is one interesting drawback nowadays with the scaling. I will be happy if one of you can tell me what you may feel. Just look at this value, 1.25 volt.
VGS is nowadays very low.
VGS. Why VGS nowadays is very low?
VDD is
because VDD is very low. Right. So now see, yeah, right. So what's the problem? The problem is that I have a VDD of 1 volt. Now I want to generate a reference of 1.25. So that is the only problem. But still there are solutions for that. Just I will show you one of the solutions. This is a very simple circuit for basic circuit which was developed. Now there are many derivations of this circuit. But look at this basic circuit. What we wanted to generate, one was VBE1 minus VBE2, right? We wanted to generate delta VBE, as I wrote for you, okay? So look at this loop. If I put an op-amp, this op-amp forces this node and this node to be equal, right, in voltage. So then I have a loop. And if you look across R2, I have VBE1 minus VBE2. I have difference of these two VBE. Agree? Clear? See, this node and this node are same. Same in the sense that they have same potential. Physically they are separate, but they have same potential, which is forced by this op-amp. So this is a loop, right? Reaching here, and this voltage difference is 0. So voltage across R2 is difference between these two VBE. So in this way we can generate that difference. And then output voltage is the current through this resistor, the drop across this resistor plus this VBE, right? So that relation I wrote for you, say alpha 1 is 1. So it will be VBE plus alpha 2 VT ln, okay? So how it is generated here? This is that delta VBE, so it will generate for me that VT. Also it will generate a current. This current will flow through this, and these two currents are same. So let us write it for you. So we have these two transistors. Okay, we had some constraint. One was to have same IC, right? Generate VBE1 minus VBE2, right? And then generate VBE1 plus some alpha into VT. These were three constraints if you want to generate a bandgap reference. So let us go one by one. How to generate same IC flowing into two bipolar transistors. This is easily done by making R1 equal to R2, right? If R1 and R2 are equal, because they have same voltage drop, so then these two current will be same. So this will be IC, this also will be IC. So this is done. We want to generate VBE1 minus VBE2. So area of this transistor is n times of this. I will show it by 1 and n. By the way, the same logic which we applied to MOS is valid here. This transistor has more area, so it should be connected to R, because the transistor which has more emitter area will have less VBE. So then this loop will be valid. Okay, so how do we generate VBE1 minus VBE2? By using this op-amp, which generates a virtual short circuit between these two nodes. So these two will be at the same potential, but they will be separate. So in this loop, if you write KVL, potential across R will be VBE1 minus VBE2. Or absolute value I put because these are PNP transistors. And one more thing, we need to generate this term. which will be actually our band gap. This we will do, so this is output voltage. Now look at output voltage. V out is equal to R1 IC plus, I write VEB1 because it is a PMOS transistor. And what is IC? IC is determined by the voltage across R divided by R. So IC is, what is voltage across R? Is VT ln N, right? Because it is delta VBE upon R. This is actually delta VBE, which is VBE1 minus absolute value of VBE2 divided by R. Now if you replace, V out is equal to R1 upon R VT ln N plus VBE. So that relation also achieved. One thing you keep in mind, here we have one VEB in the relation, that's very interesting, and then we generate some coefficient multiplied by VT to get that value of band gap. Okay, keep it this mind. So this is VEB plus some value multiplied by VT. That's why our reference is above VEB. I mean, definitely it will be above VB, and it is shown that it will be around silicon band gap 1.2 volt. Now, what is the basic idea here? Let's see that we use reverse band gap voltage principle, RBVP, instead of band gap voltage. Instead of adding a coefficient of VT to VBE, a multiple of VT to VBE, we will add attenuated value of VBE to VT, right? Now we expect to get less voltages. So now if you look, our reference will be an attenuated VBE plus VT ln N. So we won't use a multiple of VT. We will use VT ln N, no multiple, just ln N, but attenuated version of VBE1. So now the reference will come down. And it is shown that that reference now will be just 200 millivolt. So this circuit can generate references with a value of 0.2 volt. So I have written the relation here. I just analyzed the circuit once, I wrote the relations and I got this. Because one thing, just as a common advice, when you read a paper, don't trust the relations which is written in the paper. Derive the relations once by yourself. Because there are many cases in which there are some small mistakes, even typing mistakes only, but that may lead to some wrong concept or wrong understanding of the relations. So it is very easy to derive relations here. Even for the first case, you just neglect base currents, and actually that is very interesting. Look how it is working. Now we want to have just VT ln N. We don't want anything else, right? So we want just delta VB, nothing else. And then attenuated version of VBE. So this is done by this voltage division, right? Because see, this is the output reference. And now again, if you look, we have again a loop. This is our loop. So if you look at reference is this VBE plus this voltage, V1. And to get value of V1 will be this drop, which is a function of this, plus this VBE itself. So if you write it, just KVLs and replace the relation for I versus VBE, you will get this. For the sake of simplicity, first you neglect the effect of IB. Suppose IB is 0. Then these two currents will be same, these currents will be same, and then you will get this simple relation. I mean, automatically it will come. And K is ratio of R1 upon R2. R1 upon R2. Now again, by keeping temperature coefficient equal to 0 at 27, you will get the value of 200 millivolt. This relation again will depend on how these two parameters are changing with temperature. The same analysis is valid, that is valid for 1.25 volt and is given in all textbooks. So this was a brief lecture just to give you an idea of what is bias generation, and then one example of recent work, how people are trying to adapt bias generation with the scaling. So any question?
What is the reference book which you are using?
Yeah, this one is Behzad Razavi book. That is a very comprehensive reference, and it has a bandgap reference. Essentially, it has a reference generation chapter. In that chapter, you can find all this concept of bandgap generation with details. One is Behzad Razavi. Ken Martin book also is a very good book. It has also the same thing. Suppose if you want to generate a low voltage bandgap, one approach of course is given here. Another approach is, what they do is that in the conventional bandgap, they use transistors for mirroring currents instead of resistors. And now because putting transistor here as a mirror, they can mirror this current everywhere, right? They can mirror it, they can have different mirrors. So what they do, they mirror the current and then they give it to a resistor. Now what they do is that in the resistor, they give it to a resistor and to another transistor. What they do is that instead of making that VB plus VT here, they make it outside. And then outside they adjust the values in such a way to get a value of Vref less than 1.2. They call it reference-based bandgap generation, current-based bandgap generation. But actually that is only because here they mirror the current outside, they give it to the outside branch. There are other things like when VDD scales, so this op-amp should be able to handle this node voltage. So common mode input of this op-amp should be in such a way, range of input, to be able to handle that low voltage here. So that's why design of this op-amp at low voltage also is not very straightforward. So there are again different methods. What they do is that they use a resistor division here to change the voltage here. And I mean there are many things, I don't want to enter into it, but there are many patents also related to this bandgap reference generation, and each one of them there is a claim that now sensitivity even is less. Because see, even bandgap also alone may not be able to handle all accuracy we need, specifically for ADCs. For design of an ADC, definitely we need proper way of trimming. Trimming usually is done by laser and it is a costly process after fabrication. But it is required for all type of ADCs. But there is a lot of research going on how we can do all this trimming on chip and make the circuit to be quite robust. But after all, if you look at all these things, there is a very big issue in the transferring the current across entire circuit, because everywhere we use mirroring, and then mirroring itself adds a lot of inaccuracy into the reference chain distribution. So it's not only the matter of generating a proper reference, it's the matter of how to distribute it across chip. And that itself is a problem. Even an ideal reference generator, we are not able to distribute it across the chip. So that's why now by increasing the size of circuits, increasing the density, we need a larger area to distribute the bias. And as soon as we increase the area, then we will have more variation from one side of the chip to another side. So these are all new issues that have affected distribution of reference. It's not only reference generation. How to distribute, what is a proper scheme for reference generator or reference repetition. We may have something like we have in the clock distribution. We may have a repeat of a reference generation at different areas when we want to have a supply for a large area. we will create a duplicate of this reference again in somewhere else.
Why?
The reason is that because suppose I want to transfer a current from point A to point B, and there is a huge, not loss, variations. So what I do is that I will transfer it from A to B, A to C, I will duplicate this there, and then again I will transfer from C to D. Yeah, there are many issues. First of all, like what is the process we are working with? How much is the amount of variation we get across that process?
How much variation the circuit can tolerate?
Yes, how much accuracy do I need? Suppose, for example, I need, say, 1% accuracy. Of course, 1% is a very ideal value. Say 5% accuracy. And I know that my process, if I go from, say, if I start moving from point A to point B with a distance of 100 microamp, I will observe that I have 5% variation. So I will stop. I won't go beyond 100 microamp. So we should have enough information. Actually, that was a good question. One thing which is very important and usually is not given unless we are in industry is that how much is the performance of the process itself with respect to variation. If I have enough knowledge about the variation in the technology, then I can adjust my design. If I don't have, then I should go with some estimation. And then when I go with estimation, if I am overestimating variation or underestimating variation, that heavily will affect on my design effort. If I underestimate variation, I will have a fast design, but then final performance won't be proper. If I overestimate, then a lot of effort I have to assign to make a proper design, and then repeat it and compensate it, but unnecessarily, because after all, I have overestimated amount of. That's why the good knowledge of amount of variation is very important when you want to do a proper design. Yes?
Technology dependent?
Yes, it depends from which vendor you are getting the technology. Suppose you want to work at 130 nanometer channel length technology, and you are dealing with some vendor which is giving you this process. After all, you want to fabricate your chip by that vendor, right? By that fab. So the information that fab is giving to you is very important. How much information regarding variability fab is giving to you? That heavily will affect on your design. But it's very, crucial. Till now, the best practice was they would give the corner, worst case variation. And everybody was trying to design a circuit in such a way to satisfy all desired specifications across all process corners. But now with the scaling and a lot of variability issues, this methodology is very costly. It takes a lot of time. You need to consume area and power to satisfy all the specifications, and so it is very costly. So that's why it would be better to have a better information regarding variability, rather than worst. Corner actually is an overestimation of variation and considering a worst case scenario.
Range of reference voltage, as I said, 1.25 as we were taking the case of ADC.
Yes.
So if we want to have below that or...
Yeah, then we should convert it. Yeah, there are circuits by which we can convert a DC level to another DC level. That is done afterwards. We generate that reference and then we will use that converter to generate new levels of voltage.
Basically, we start with 1.25.
Yes.
Whether you need more or less.
Yes. That is something which is naturally we get from silicon. Yeah. So it is preferred to start with that and generate everything out of it. Of course, now we can generate smaller values and then still generate other values that we want.
Because when we are adding to the 1.25, we want to have something else, we are adding the circuit. So that requires additional...
But that is okay. See, one thing which is not as such important in supply generation at least is that if I can sacrifice area because of accuracy, that is okay. Because that is the fundamental circuit which supplies the entire chip. That is fine. But for other modules, of course, we are worried about area. So that is not, that conversion is not overhead on the design. as long as that converter doesn't dissipate power. A lot of power overhead on the design, which is not usually the case. It might be the case, but not in always. Specifically, if you look like in data converters, reference is given usually to the gate of transistors, which is not drawing any current. So we don't need to generate a reference which will drive a heavy load. So that makes the design at least easier from this aspect. But as I told you, it's not only a matter of voltage level, it's a matter of noise. So all these circuits should be low noise nowadays. And better accuracy, getting better accuracy from band gap. It's very important. For the using current method, which is using current, nowadays people are generating 0.6 volt instead of 1.25 volt. Using that, mirroring the current and then give it to an external resistor and then series with 1 VBE, they are generating 0.6 volt. So at least these three values they have reported and they are using. And it is good enough, at least for today's applications, 0.6 volt is good enough.
So what about the noise control?
Yeah, noise is very important. Because suppose you have a reference which is having noise, and that noise is not small, say in the range of millivolt, so your noise will reach to the LSP size of ADC, and that will affect on the accuracy of ADC. So for ADC design specifically, we are much worried about this effect. So it should be a very, I should call it low noise reference generator. But for some other, it depends on application. But I would say that ADC is one of the stringent applications. For that, we need a low noise. See, for example, a simple example of mirror. Suppose you have two transistors, gates are connected, sources are connected, and just drains are different. So we say that if these two transistors are working in saturation and one of them is conducting a current ID, the second one also will conduct current ID because they have same VGS, they have same VT. And now if you increase the distance between these two transistors, their VT now will be different. So even if you forget about output impedance, which is one of the sources of inaccuracy, still this variation will be a source of inaccuracy. And of course, I mean, that output impedance issue is there. So that's why we never use these simple transistors in the common source. Always we use at least in cascode configuration.